Okay, hello everybody and welcome to the ElmerFEM webinar series. This is the second time we have this series. This will be a shorter stint. So we started already the series. We already started the webinar series last spring. We had a series of 9 different presentations and they were quite popular, and especially they have been very popular on the YouTube, so the presentations are available there. Now in December this year, we will continue with 3 additional presentations. So Jonathan Velasco will start today. Then we will have one from Thomas Stringer and myself on the following weeks. And these will be recorded and be made available again in YouTube, and the slides will also be made available at Nick Funet FI server. During this presentation, you may ask questions, and Jonathan will answer them then in real time. With those words, I will give the floor to Dr. Jonathan Velasco. He holds a PhD from the University of Leeds in electrical engineering, and he has now been a member of Elmer team for the past year. So please, Jonathan, you may start the presentation.
So hi, my name is Jonathan Velasco. Welcome to this webinar. As my colleague mentioned, I will be talking on how to model coils using Elmer, but particularly I'm going to address a tool we just recently implemented called the CircuitBuilder. So welcome. So what is the CircuitBuilder? Before we jump into it, I just want you guys to understand that the CircuitBuilder is not a solver. It is a pre-processing tool. So it is simply a Python module to automate circuit matrix creation based on circuit connections. So terminal pins, 2-pin connections. So if you actually look to the right, you're going to see an image of a quasi schematics. And for instance, here we have a source that is connected between pin 1 and 2, a resistor, which is connected between 2 and 3. And then we have an Elmer component, which is connected between pin 3 and 1. Now, here what we do is we're coupling 2 things, right? Because we have the lumped parameters provided by the circuit, and it will be coupled to an actual coil finite element model. And these components that you see here can be ideal voltage sources, ideal current sources, resistors, inductors, or capacitors. And then the types of coils we have available for you guys are massive, which means simply it's completely solid. So what you see in orange is solid material. In this case, let's assume it's copper. Then we have stranded, which would be this image to the right. It doesn't have to be circular coils, but you get the point of it's a multi-turn winding, let's put it that way. And then the foil, which is basically just foils in the same fashion. You have multiple turns. So what type of problems, what kind of problems are we solving with the CircuitBuilder? With the CircuitBuilder, we're not really solving the problem itself. We're using Elmer for that. However, this helps us to set up the problem in an easy way. So what we're trying to do is set up problems that are basically current conducting coils in 2D or 3D, and they're coupled to electrical circuit networks. And then the coil models will be solved by the CircuitsAndDynamics module. So there's where you set up if you want a massive, stranded, or foil winding. As I mentioned before, the massive is solid conducting material, and the other 2 are homogenized, so you don't explicitly make every winding of the stranded or foil winding type of coil. And then we solve the magnetodynamics AV formulation to solve the field problem. So you see it's a circuit field problem. Those are the problems we're trying to set up with this. But before we jump into it, let's just do a little refresher of how the source input file in the Elmer looks like. Some of you might actually have used Elmer before, and you're familiar with this terminology. If you're not, I definitely recommend looking up the webinars that we did earlier this year to get up to speed. And I'll try to just work through this very slowly so you understand what we're looking at. Here, basically, we have what we have in any finite element code. We need to define certain things such as what are the domains we're solving, what are the equations we're solving, and what are the parameters we want to include in our formulation. What are the material properties, initial conditions, boundary conditions, and so forth. So those are the sections that you see here to the right. And then, of course, you need certain other types of you need to assign other structured blocks within the file that, such as the type of simulation and well, that's about it. And each variable will have a different type, so you can cast them directly in the CIF file. So it can be real, it can be integer, logical, string, and file. Before we jump to the next slide, sorry, I will be focusing, or rather, the circuit builder will be focused on these two blocks, which are the body force, which, if you're an electrical engineer, you probably know it as the external source. So that's how we apply either a current or a voltage-driven problem. And then we have the component, which is what will allow us to couple the circuit to the finite element model. Once again, if you haven't seen a CIF file, this is what it looks like. So it's exactly what I explained before. You start with a header, which simply points to the mesh file. And then you have a simulation block where, depending on what you are solving for, if you're working in steady state, on transient model, time harmonic, you specify it here. And then, of course, depending on the type of simulation, you will have to specify particular keywords applied to that. Then you have the body. And which is the domain you're solving, and you apply the equations you want to solve in that particular body, and the material. The equations, which is simply the sequence of solvers that you're going to use. For instance, in this particular model, we're only using solver 1, which is just a PDE. Material properties, boundary conditions, etc. So it's really straightforward. So how does this work along with the circuit builder? So we first need to go back and address how circuits are built within Elmer. So the coil models have been implemented for a long time, but you have to build the circuit so-called matrices. What are these matrices? You need a stiffness matrix and you need a damping matrix. And the way this is associated with each other is that the ones that, for instance, if you see the image to the right, you're going to see that you have CKT, which is the circuit file, and then you have something called the CIF file, which is the Elmer source input file. Now, as you see, some of the things we're defining will be exclusively defined in the circuit file, and other ones will be defined on the CIF file, and some of them even in both. So how do we go around it? So here, basically, is the explanation of what I just said. In the circuit matrix, you need the source, the electrical components, and the coupling factor between both the finite element definition and the circuit. And then in the CIF, you need the coil model, and you need the body force. So that would be split into basically the image that you see here, where this little part over here would be the source, would be the lump parameters, and this part is the finite element problem, which is coupling with the component. What we did with the circuit builder, what I explained at the very beginning, we're taking each individual component and we're actually defining everything under a single umbrella, which is the circuit builder. So instead of knowing if you need to put it under the circuit, definition, or you need to put it in the CIF file, you put everything under the same Python script, and then you develop, you create these matrices. How do we use the circuit builder? So it's fairly easy, and I'm going to do a demo later, but just so you know how it works. So you first need to use Python 3 and an editor An ID is not needed, but encouraged, meaning all the information in documentation is within the code. It's in doc strings. So evidently, if you are using an IDE, you will definitely benefit from it. How do I install it? So this is in PyPI. Simply by typing this on terminal, pip install Elmer CircuitBuilder, you will be able to download this module and be able to use it in your setup. And how do you set it up? So here, I'm just gonna read out loud the steps, but then I'll simplify the problem in the next slide. So first, we're gonna import the circuit library. You're gonna set up an output file name. You need to set up how many circuits you're gonna have in the problem, assign a reference node, and then add the components to the circuit, generate the circuit, and make sure that once you output, the output file that generates the circuit builder generates needs to be included in the zip file for it to work. So, as I said, it's a lot of steps, and if it's the first time using it, it might be confusing. So let's just look at the main template. And the main template is actually added in our GitHub repository, and I will go through that later. But basically, it gives you all the steps that I mentioned earlier in this particular template. So for instance, here we have step 1. You include your library. You need a name for your output file, how many circuits you're going to have in the problem. So you can do more than one. Reference node. You assign all the components that you need. Assign the type of coil you want to model, if it's massive, standard, or foil, if it's 2D or 3D. And it's also very important that you assign if it's a closed coil or an open coil, and I'll get that into that later so you understand the difference between the two. And last but not least, you're gonna include all the components you defined up here in this list. And by running this Python script using all these steps, you will generate the circuit files needed to model that particular problem. On the right side, as I mentioned earlier, using an IDE is definitely encouraged because the documentation is there. So for instance, here, I have this coil definition, which is simply an object of Elmer component. And here you see the documentation, so you know what the parameters are and what they're casted as, and the description. And here, this is not all the documentation, it's just a fraction of it, but you understand the benefits of actually using an IDE. In this particular case, I'm using PyCharm. So to define an Elmer component, you will need a name. You will need a pin 1 and pin 2, high and low, or low and high, depending on your convention. Then you need a component number, which is referred to the zip file, and a master body, same thing. And sector is set to 1, but it's for symmetry. If you're modeling a quarter of your coil or something like that, you will then multiply by the appropriate factor. In this particular case, it's just assigned to 1. So you need to change it if you're doing something a little more special. And then here we have a voltage source. So it's simply an object, which is defined by the letter V, very intuitive. And then same approach, you need a name, a pin 1, pin 2, and a value. And the value, actually, you don't need it. You can assign it to nothing, and it will be none. But then you, in the output file, will have to fix it. You will have to give it a value eventually. But if you're prototyping quickly and you just want the actual matrices, everything is parameterized, so you don't need a value in the Python script, in the beginning at least. So how does the output file look like? It looks exactly what you're looking at. So first, it starts with the date it was generated. That's just for looks. But here it tells you how many circuits you have in the model. It creates a parameter section where each individual parameter that you defined earlier is assigned to the value that you gave it to. So in theory, this is all you should modify if you want to change values in your problem, because everything else will be parameterized. Meaning, for instance, if you actually look through the matrix definition, here you see these is you're initializing your matrix, you're defining your your currents from the source going through the component, and same way you have the voltage going across the source, the voltage across the component. And then this is because of the method we're using to build these matrices, which is called tableau method or tableau analysis, if you've heard of it. So this is just a nodal potential. And then here you have I1 is the source. You have your Kirchhoff current laws and voltage law equations, your component equations. And then here you have the additions that go into the zip file, which are the component block that I talked about earlier. And you have the body force, which I also talked about earlier. As you see here, this is actually parameterized. So here you see I1, it refers to this I1 variable I defined earlier. So if you want to change the value, you can do it over here. If you have a time dependencies in your sources, you will have to make a couple of tweaks in the zip file. So for instance, if you're working with harmonic in a harmonic simulation, you will have to add in the simulation block the angular frequency. And then if you're working in transient, you will have to go to the body force and add whichever function describes your transient. In this particular case, I just have an amplitude and a sine. So if it's a current or voltage, this is how you would set up. And I'll go over that again once I actually go through the code. So let's go through a demo so maybe you understand a little better. Here I have a quasi schematics again with a sinusoidal source going through a stranded coil. So basically it would describe this problem I'm looking at to the right. You have simply a source going through this is what I would call a closed coil because it only has really, we make a cut and then we add the discontinuity there. So you only need to define one value. It's not an open coil where you would have two terminals. I know this might be confusing now, but later I will show you some additional figures that will explain better. Let's go to the demo. So this is the template I showed earlier. And here I have two, well, for the demo, I will go through two types of simulations, so harmonic and transient. We're only going to compute the transient for time reasons, but I will go through everything as I explained earlier. So you not only see the webinar as a source of information, but also you can use it as a tutorial for beginners. So let's go step by step. So we have step one, which, as I mentioned before, is just include all the functions that are in our Elmer CircuitBuilder. So then we give it a output file name. So I'm going to call it harmonic team 7 circuit definition. And then I'm going to assign the number of circuits. In this particular case, you only saw it's a single current source connected to my circuit. So I'm going to leave it at that. And I'm going to leave my reference node as 1. So let's go ahead and define some components. Because this is a harmonic problem, and I'm going to open here the directory so you see what we have in here. So here, actually, let me delete this. This is an old circuit definition. Okay, so we have the main, which is this template that I'm working on, and then we have the zip file. And okay, so I will go to define the components now. First, I'm going to define a current source. I'm going to define a current source called IS, which is an I object. And I'm going to just call it the same name just for simplicity. And here, as you see, this is why I advise, encourage using an ID. It tells you what you need within the class. So for instance, here, we assign a name as a string, then we need a pin as an integer, a pin 2 as an integer, and a value, okay? So I will go.
Jonathan, people cannot see the code, they see the pictures.
Oh, well, I'm glad you're telling me now because we're halfway through this. Let me see. How do I change the, let me see. Oh, I'm so sorry. If I stop sharing, how do I? Okay. Thank you for letting me know. Do you see it now?
Yes.
Okay, thank you. Okay, so I'll recap just because you weren't seeing this before. So here I have a harmonic directory, which is the harmonic problem I'm trying to solve. I have my team 7, which is the name of the problem I'm solving, or a version of it rather. This is the source input file that Elmer needs. And this main py, this Python file, is my template that I showed earlier. So I'll go through the steps again. So the step number 1, I imported my library. Then I gave it a name for the output file that I'm going to use in the zip file. I add the number of circuits. In this particular case, as you saw earlier, it's just one circuit. Then I have the ref node. And then let me do this once again. So I'm going to assign a component. I'm going to create a component IS, which is my current source. It's an object I. And here, as I mentioned earlier, what I like about using an IDE is that here you can see what the object needs, what the class needs. So here I'm just going to go and call it IS just for simplicity. It's going to be the same name as the name of the variable. And then I'm going to give it 2 pins. So 1 and 2. And then I'm going to give it a value, and I'm just going to put 2742 plus 1J. Let's just multiply it. Well, actually, I'm going to multiply this by 0. So it's only the real part. But this is, you still need the real and the imaginary part if you want to compute it with, if you want to solve the harmonic problem. So I'll give that there. Okay, and not because Elmer needs it, but because the circuit builder will need it, because it splits the real part and imaginary part. And you can, obviously you're working in what is called, with Python, so you can also do, you can follow the Python rules. So if I wanted, for instance, to make it a little prettier, maybe. So import numpy as MP. I could, for instance, here create a variable called face, and then just use it here instead of doing this ugly expression. So it would be np exp j, and of course it will be minus or plus depending on the convention. So here, this is my current source. It's the name, the pins, and the value. Straightforward. Now we're going to define our next component, which will be an Elmer component. So let's just call it FEM component 1, which is an Elmer component. And here we'll just call it coil 1. As you see, it doesn't have to be the same name. I'm just here I give it just for simplicity. So here's coil 1. This will be connected between 2 and 1. And then here's is where it gets tricky. You need to be aware that this needs the information from the zip file as well. So this is the name of the component. These are the pins to which it's connected to, but then you will need the component number. So because this is the only component I have in this problem, I would call it 1. And then I will just add a list where I'm going to assign the bodies to which this is associated to. So this is the component number, and this is the body, the master bodies, if you're familiar with the Elmer lingo. Okay, so those are our 2 components, electrical components, but now we need to assign a couple more definitions to the component itself. So the first thing I'm going to do is just make sure that it's stranded. I'm going to actually not do I'm going to use the stranded function method rather, but I'm really just going to assign 1 turn and no resistance. So it will basically work as an external current source. It will compute faster for the purposes of the webinar. And then I will assign here the dimensions and if it's closed or open. So we can just go ahead and component is 3D. So by default, it will be 2D, so you don't need to do anything if you're working in 2D. And then same thing with, and then it's closed. So that's all we need. And then we need to add these components to this list over here. And that should do. So as I mentioned before, let's recap. We created a name. We said how many circuits we're going to have. We created the components we need and specified if it's 2D or 3D, if it's closed or open, and we appended into the circuit definition. So now if I run this, okay, it will create this output file. And we can actually take a look at it here. So it's I generated this circuit just now. It has one circuit. These are the parameters. So as I mentioned before, this will make the splitting between the real part and the imaginary part. And here you see the face. So you can play with the faces if you need to. The parameters needed in the component. Right now I have this electrode area, just a dummy for legacy purposes, but you shouldn't require it now. And then you have here the definition of the matrices, the initialization. You have the components that you're solving for, the source vector, KCL, KVL, component equations, and the additions of the zip file. So you have that this is a stranded coil with this number of turns and this resistance, and this is for 3D. You will need these keywords, and then the body force. So here you have the real and imaginary part of the given source. So that's how this works. So just for, just to make it a little more comprehensive, let's just go here and maybe run the problem so you see the output as well, and not only the output from the circuit builder, but also the output from Elmer. So I'm going to import OS, and then here I'm going to go OS one. So OS system. What is this called? Team 7 harmonic SIF. And then maybe open with Coil here. So OS system. This is the actual name. So this will generate a results output, and then it will call it from there. So as you see, like now we generated the circuit, and then it's using that output file, which I had already previously included in my zip file. It's running Elmer Solver with it. And hopefully, if everything goes well, we will have the problem resolved. So while this runs, it will take maybe 2-3 minutes. I'm going to go over our repository, the LMAG repository. So here, if you go to GitHub and you look for the Elmer LMAG repository, we have a very large amount of examples, but all the ones that are related to how to use a circuit builder and how to benefit from it to model coils are under our directory with the same name. And here, it's basically all the instructions on how to install it, how to use it. It has the template that I mentioned before, so you only need to copy it here.
Jonathan, you are still on the on the code page. So
okay, maybe I should just switch it to the desktop. Can you see it now? Are you on GitHub?
yes.
Sorry about that. So here on the Elmer LMAG, you have the circuit builder. And here are all is all the documentation on how to use it, how to install it. And here's the template I talked about earlier. So if you want to use it, you can just click on this and it will be copied to your clipboard. How to create components, how does the output look? So basically everything I'm explaining here, except for this part that I wanted to address here, which is what are open and what are closed coils. So evidently, if it's completely closed, we're using something called the coil solver, and it will create a discontinuity in the coil, so you don't have to do anything. So you only need to assign one terminal, as I did just now. But if you have something that's open, it has two terminals, you will have to assign that when you're including it in the definition of the coil. And the Elmer circuit directory, I have examples in 2D and in 3D, and every example has foil coil, massive coil, and stranded coil for both harmonic and transient cases. So if you're interested in learning how to use these, there are simple examples here that are basically copy and paste that you can use as templates to get you started. And let's go back to here. So here, it finished the simulation. That's why ParaView opened. So I'm going to do some quick post-processing here just to see what we solved. First, this is going to be very quick. So we have more times maybe for questions at the end of the webinar. So this is my coil. Then I'm going to extract the plate. So we're going to have here the plate. And I think it's 3. Okay, so we have our coil and the plate that we're solving for. I'm gonna go ahead here. I'm just gonna plot the current density on the plate with arrows. So current density, and it needs to be scaled. So So as you see, like there's something there. Let's put some color to it so we can see it better. Current density. And maybe let's remove this. So here you see the currents being induced into the plate. Remember that the coil is current carrying coil, but we're inducing currents in the plate. So we can also like maybe just for visuals, look at the flux. So magnetic flux density. And here you can see the flux generated, the field generated by the coil and inducing currents on the plate. So that's the problem we solved. And we set up the circuit with the circuit builder. But remember, you still need a zip file. So let's go through it real quick. So if you actually go through the problem, you will go through the blocks I mentioned earlier. So you have the header where it looks for the mesh. Here I specified some parameters. And then we go here. This is a steady state. Well, we call it steady state, but it's really time harmonic. Here we assign the frequency of the excitation frequency that I mentioned earlier, that you need to make that change if you're working with this. And then, of course, you have the bodies, the domains will have a coil, air, and a plate, and they have different material properties, my boundary conditions. And this is my solver configuration. I solve first for the coil, and then I solve them together for magnetic dynamics problem. And each solver is here from solving the coil, reading the circuit, solving the AV formulation, post-processing the information in the field problem, and outputting also the circuit data. So if you actually go to the results, you will see that I not only have a VTU, but I also have data. I'm just going to show you the names. And here you see all the information that we output. So if you're interested in, you know that you input the current, but you want to check the voltage, then you just have to access this column within the, well, in this particular case, it's called F1 file. And as I mentioned earlier, like if you and this will be very, very quick. If I go to the transient problem and I go to the main, this looks exactly the same. So you define an output file, output file name, a number of circuits, the reference node, the components, if it's through D, stranded and close, and that's it. But here you need to be careful because the output will be transient, but you will have to make tweaks, remember, on the body force. So if we go here, basically when you create this, well, in this particular case, I have a sinusoidal source, but when you run the Python script, it will give you something like this. So whatever dependency or time dependency you have in the source, you will have to add it later on the body force. And that's that. Okay. So let's recap what this is. So we have that the circuit builder is a library. It's a Python module that you can download from PyPI. There's a main template that you can use, and it's in each one of the directories within our repository. You can find one called main, and that's how we generate our circuits. So you have a better understanding, and you can get started with those. Remember, if you have a transient source, it will just give you basically a DC current or voltage, depending on what you're setting up. So if you have any time dependencies, such as sinusoidal sources or any other type of mathematical function, you can set it up yourself there. And don't forget to include it in the CIF file because otherwise it will not read it. So you need to, the same name you're producing with the circuit builder, you need to include it into your CIF file. And as I showed earlier, we have several examples in our repo. So I definitely recommend going there and just getting started. And if you have any questions, you can always contact us. Or if you have any, if you're interested in maybe contributing to this project as well, you're welcome to contact me. So I guess this is time for questions. Thomas, are you there, I guess?
Yes, there are no open questions in the Q&A at the moment. So maybe people want to raise their hands. I think I saw Elis. So I guess I just unmute Elis and they can ask the question. Is this okay for you?
Yes, that would be great.
Okay, Elis, you should be able to talk now.
Can you hear me?
Yes,
yes.
Yeah, very, very nice. Thanks for the presentation. It was very clear, and I see that you have done a very good job on this one. I have been actually waiting for this for a while, that when this happens, because we should never underestimate the importance of user interfaces, and I think this is a very nice job for building the electrical circuits. Now, the next step, I don't know if you have any plans or if Elmer team has any plans further, but I was thinking that could there be some integration with Elmer GUI or something like that to integrate this further into some graphical user interface, or do you have any other plans?
In the short term, we're not currently working on that, but yeah, eventually, I think, because basically now we did part of the work, we developed a data structure that is readable by Elmer. So if we could possibly, I think the easiest way would be to maybe interface with schematics tool, maybe open source. And so we're looking into that. So hopefully in the future, it will be there.
So schematic tool, you mean that you could draw these circuits with
that would be ideal. And if someone in the audience has experience with that, it's welcome to maybe contact me and we can work together on that too.
Okay, thanks.
I further saw earlier someone else raising their hand. I think Marco. Yes. Marco. Okay, I will switch you free, Marco. You should be able to broadcast now.
Can you hear me?
Yes.
Yes.
Okay, great. First thing, thank you for this amazing software. I'm very glad it went on through the years. I saw it developing and growing, especially the electromagnetic part. Very nice. Furthermore, I wanted to ask about this solver. So I was trying. I didn't understand well. This the problem that you showed here, is this stranded? It has already strands in it.
Yeah. So, how I set it up, it would be a replica of using an external current source. But yeah, so basically how it works is that, and maybe I can show you rather, because I didn't talk about that because I didn't want to spend too much time on that. Mm-hmm. But basically when you're working with the coil models, the stranded and foil are actually homogenized. So you need to basically set it up as a solid material. Yep. And if it's stranded, it belongs to the non-conducting domain, for instance. And then so you model it as air. And then if you're interested in the actual numerical part of it, we developed it based on these references that you see here.
Mm-hmm. Mm-hmm. Well, so, yeah, sorry to interrupt. Rather than talking about the details, I was wondering, for example, if I want to have, I don't know, 100, I want to have 100 strands, maybe, yeah, okay. I see the point. Maybe we are
so basically, if you want 100 strands, you would go here where you said stranded and just have 100. Add your resistance of whatever value that is. Maybe you have a DC resistance here, maybe of a particular value. Let's just say 1, and then that would be it. Then you have a stranded coil with 100 turns with this DC value.
And that is a coil with 100 turns. Okay. And what about the resistance? Do you need it, or because this is something that I mean, if you set it down, if you don't have a prototype with you, you really don't know exactly the resistance. Do you need to put it there? Is it required, or can you estimate it somehow?
Well, you estimate. Usually, what you do is that you do either the AC or DC resistance for a single coil in or a single strand in isolation. So, for instance, that's the rule of thumb that you do, and that's I would recommend to do it, because otherwise, like I did it for this particular problem, you are just inputting flux basically.
Okay, I see. All right.
Any other questions?
If I can, a really trivial one. Is this altogether the package? I mean, the Python and the interface and the main everything. Is it already available in a virtual machine? So if I download the virtual machine, will I get all of this already installed and ready to run?
No, you would still have to download with pip, but I think we can definitely fix that. We can definitely add it in.
It would be interesting. It would be interesting to see that.
Okay, let me see. I think someone asked questions. I don't know if maybe he wants to speak, or I can read it out loud. Sorry, Marco. Do you have any other questions?
Perhaps, but it's not important for the moment. Let's leave the others. I don't want to. Please, by all means. I mean, these were the most important were there, I think, from my side.
Okay.
Yeah. Should I read the question?
Yeah, you can read it.
Yeah. Okay. So Martin is asking to what extent you are considering nonlinear components.
Yeah, right now, I think this is a very important question. Right now, we only have linear components. I think with some skill, I guess you can definitely use, for instance, a variable resistor if you can code in Fortran and make some modifications. But it would require some effort for sure. It's not readily available at the moment, but it's definitely something that we're currently thinking about improving in the current setup.
Martin, do you want to have a follow-up question? I can shortly unmute you, or is this okay answered?
Okay, I'm online now. Yes, the problem, of course, is that in electrical engineering, there are no linear components. All components are more or less non-linear. So I was just asking whether this has some priority at this moment. So my question is was answered.
Yeah, evidently, obviously, it would be ideal to have maybe some IGBTs or something like that, some switching components. And as you said, right now there's nothing readily available. It would require some effort, but it can possibly be done. But I guess we'll just follow us on GitHub and maybe hopefully sometime next year we'll have something. I don't know.
That would be nice. Up to now, Peter already helped me with this.
Okay, if there's no other questions, then I'll just move to the next slide. Okay. So as Petr mentioned in the beginning of the webinar, this is not only a single webinar, we'll have a series of webinars. So our next webinar is on the 15th of December, and it will be focused on geophysical applications, particularly but not limited to Elmer ICE. And the physics focus will be on viscoelastic modeling. So the earth model you see to the bottom left, and bedrock permafrost modeling. So the model you see to the bottom right. And the registration link is the same thing, the same one you used for this particular event. So just click on it and register right there. And please, if you want more information about Elmer, don't hesitate to go on our website. There's a lot of information and examples there. If you have questions, particularly related to this topic, still don't send me an email directly on this. It's something very particular. I would rather have you go to the forum and post them there and then ping me if you can, because then I can take a look at it. And if there's good answers there, other people can benefit from those. Check out our repository. Obviously, our source code is there, not only the ElmerFEM, but also the circuit builder that I mentioned earlier. We have our YouTube channel, so we have animations and we have some webinars and installation tutorials there. And this webinar will also be there next week. So I definitely recommend you to check it out. And then, yeah, and that's about it. So thank you very much for having attended this webinar, and I hope you enjoyed it and we'll use the circuit builder. Bye.